In this video, we're going to take a look at how to determine the polarity of molecules overall. So far, we've been looking at the polarity of bonds, but when we want to determine the overall polarity of molecule, we have to consider the symmetry and the shape of the whole molecule. And then we also have to look at all the bonds within the molecule. So we have to look at all the bonds within the molecule. Are they polar, non-polar? And then look at the symmetry and shape and make a judgment call as to whether that molecule overall will be polar or non-polar. So one important point to note here is that it is possible for a molecule can have polar bonds and still be non-polar, because again, you need to look at the overall shape of the molecule to determine if those polar bonds overall will make your molecule polar or not. So you can still have a molecule that has polar bonds and still be non-polar. Let's take a look at some examples. So here we have the molecule CO2, common molecule, very straightforward. This is our Lewis structure. And if you were to calculate the electronegativity difference between the C and the O, I'm just going to draw the lone pairs there, you would see that the bonds are polar. We did it in the previous video. We saw that C and O is 1.0. So 1.0 here and 1.0 here. That's a polar bond. And oxygen is more electronegative, so the dipole would be towards the oxygen. And it would be the same thing on the other side. This dipole here would be towards this oxygen. So we have two polar bonds. This is a polar bond, call it PB, and this is a polar bond, call it PB. However, overall, what I want you to notice is happening here is because the dipoles are pulling in opposite directions with equal force, since it's the same atom on both sides, essentially, it's symmetrical. These dipoles are canceling out. So the dipoles cancel out, and we say there's no net dipole. Therefore, the molecule is nonpolar. So even though carbon dioxide contains polar bonds, which are here and here, overall the molecule is nonpolar because the dipoles of the polar bonds cancel out since the molecule is symmetrical. These vectors, these arrows, when they go in opposite and equal directions, they cancel out. And because they cancel out, there's no overall direction that the electrons are going in. There's a nice equal distribution, even distribution throughout the molecule. Now, in some cases, the dipoles do not cancel out. So let's look at water, H2O. In this case, you'll notice the shape is not linear. The shape is bent. And you'll notice that the OH is a polar bond with the dipole pointing in the direction of oxygen. So you'll have a partial negative charge here and partial positive charges on your hydrogen. And notice that the vectors, the dipole arrows, are not going in equal and opposite directions this time. So they won't cancel out. So there will be an overall dipole. In fact, the overall dipole is just pointing towards the oxygen. So from hydrogen to oxygen, with the oxygen end being the partial negative and the hydrogen ends being the partial positive, as you can see there. And so if you understand how these vectors add together and cancel out or don't cancel out based on the symmetry of the molecule, then it's fairly straightforward to determine if your molecule is polar or not. But you have to analyze the bonds within. So this is a great visual to go over before we continue going forward. Here we can see some dipole arrows drawn for aluminum chloride. We have arrows pointing towards Cl, towards Cl, towards Cl. And what you'll notice is that since they're all pulling in equal and opposite directions in a symmetrical way, they're going to cancel out. And so how do we do that? What we do to figure out if they cancel out is we add them head to tail. So notice I have the purple arrow here. I put the green arrow, I connect its tail to the head of the purple arrow, and then I connect the tail of the red arrow to the head of the green arrow. And notice how they all end up meeting up again. This means they've canceled out. And so overall, this molecule is considered nonpolar. Whereas if you look over here at this SO2 molecule, when I put the two arrows together, so if I put them together head to tail, they won't cancel out. And let me show you what it looks like if we draw it. So if I put the two arrows we saw there head to tail, so one was going this way and one was going this way, notice that they don't meet up at the end like the other one did. In fact, you have a spot left over here, and that would be called your resultant. This is your overall dipole pointing in this direction, for example. So that's what we see over here. These two vectors over here were added together to get an overall dipole. Whereas these three vectors, when you put them together, head to tail, head to tail, head to tail, they meet up and close off, and that means they cancel out. Same thing with this one over here for carbon dioxide. If you add them head to tail, if you put this head on this tail here, they just run back and forth on each other and they cancel out. So the resultant is what's left over, and it's your overall dipole. If you've done some math in grade 12, this will be very familiar to you. And here we can see the visual we were looking at before. We add the vectors head to tail. So these two can be added head to tail, and you get an overall final vector over here to show you the direction of your polarity. Let's go take a look at that on our drawing here. So I'll take a look at the two arrows there. So when I add them together, these are the two arrows we have here. I'll do one arrow like this, then the tail of the other arrow here, and then what's left over is this, and that's my overall dipole direction as we draw it here towards the oxygen. Now, we won't always have to draw vectors out like that every single time because it's not always as simple. We also have 3D shapes that make it more difficult to draw vectors out. So we just need to become familiar with what shape is considered symmetrical, where cancellation will happen, and what shape is not symmetrical, where cancellation won't happen. So again, the idea is if you have a symmetrical shape, vectors will cancel out and you'll have nonpolar. If you have asymmetrical shape, the vectors will not cancel out and you will be considered polar. So this is a little table over here that you can take a look at to see what is considered symmetrical. Notice a linear molecule is considered symmetrical as long as the atoms on both sides of the central atom are the same, X and X, for example. So overall, you'd have a nonpolar molecule even if you have polar bonds. However, if you're linear and the atoms on both sides are different, like an Y there and an X there, overall your molecule will be polar because, yes, they're pulling in opposite directions, but it's not with equal force. For the one with the atom that has greater electronegativity on one side will have a larger vector, so it won't cancel out. If you have a bent shape, that's typically polar because it's not symmetrical. The little vectors here will add up together to give you an overall dipole. If you have trigonal planar, these, as long as the x's are all the same, of course, will be considered nonpolar. But as soon as you have a different peripheral atom, then you're considered polar because you're no longer pulling with equal force in all directions. If you're tetrahedral and all your atoms are the same, X, 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 and X is symmetrical, and we have a cancellation of the dipoles even if there were polar bonds. However, again, as soon as we change one or more of the atoms, it becomes polar overall. A trigonal pyramid is typically polar when you have polar bonds. And what you can do is you can take a look at a flow chart. And a flow chart like this one here can help you determine if you have polar molecules or not. So in this video, we saw that molecular polarity, to be determined, you have to look at all the bonds in a molecule and whether the molecule is symmetrical or asymmetrical based on the shape. If the molecule is symmetrical, it means that the vectors will cancel out and your molecule overall will be nonpolar even if there are polar bonds. If it is asymmetrical, meaning not a symmetrical shape, then the dipoles will not cancel out. You'll have a net dipole, and the molecule will be polar after all. And so we saw some examples of what constitutes symmetrical shapes and what doesn't constitute a symmetrical shape, and when things will be polar. And then in the next video, we're going to do some examples using this flow chart, which is essentially based on the idea of symmetry.